going, and why? You're going left because the y values are negative. And then for the rest of the time, since the y values are positive, you're going right. Now, how can I use this graph to figure out when this particle is speeding up and slowing down? How do you do it? Talk about in your groups. And I want to know the intervals. I want to know the intervals when this thing is speeding up. And then I want to know the intervals when this is slowing down.
Slowing down there and there. That's when it's approaching the x-axis.
Okay, so do you like the way she worded that? It's slowing down as you approach the x-axis. Okay? This whole thing then, like, are we going from a point? So what are the two intervals that we're slowing down?
From 0 to 1.153.
Okay, let's write that in interval notation. I'll write it here. You say it. 0 to 1.153.
And then from
Union.
I mean, what point did you say
It was 2.13.
2.13
Okay.
until,
What is that? Is that the min?
yes.
Okay. 2.13 what?
Well, it was 2.12728.
127?
128.
3 decimals. Just get in the habit to right now. Okay. So you calculated the min, and that's a time of 2.128. So then you said union
Is 2.128 to 3.18.
Okay, do we agree with that? Yes? Okay, very good. Thank you very much. Alright, again, the other way to look at it is the velocity is positive here, but the derivative of this is going to be what? Negative. Why? Because it's decreasing. Yeah, it's got a negative slope. You see that? The signs are different. It's slowing down. This is a negative value, but a positive slope. So its derivative is going to be positive. The signs are different. So it's going to be slowing down. Does that make sense? Over here, this has a negative value and a negative slope. So what does that mean? It's speeding up. Or as Jessica said, in this case it's going away from the x-axis. Over here it's got a positive value and a positive slope. What does that mean? It's speeding up. It's speeding up in the right direction. Okay? So what are those intervals for speeding up? And do you guys notice how I'm including the endpoints again, Amina? I mean, even though it's not technically, I include them. Why? Because that's how I learn it. Both are acceptable. This is my interval for slowing down, even though it's 0 and there, like this one's technically 0. That's technically correct. Or you can put the parentheses. That's what we were talking about last time. All right, 1.1532. What is it?
2.128.
Okay. And then union, any other intervals?
3.18.
Yeah, and then it continues on until you decide to stop, or never. It's just going to keep on accelerating until it hits the speed of light. Good stuff. Okay? Any questions on that problem? Was that it? Oh, and then when is the particle at 0.5, comma 2? For that, when is the particle at rest? When is the particle at rest, you guys? Well, it's not technically at rest, right? Because it's like it's just at 0 for a split second. Is that still at rest? Sure, you're right. Technically it is. Technically you're right. There's just that split second, okay? When that whenever the velocity equals 0, it's just that split second, okay? That change of direction. All right. And the last question was, when is the particle at the 0.5, comma 2? And how can you figure that out? Nathaniel.
You can put 5. No, you can set the function equal to 5, the position one.
Yeah, that would do it. Again, because 2, the y value is always going to be 2, and that's kind of the trick. It's like, what's this 2 doing here? The y position is always 2. You set this equal to 5, and then solve for the time. That'll make this equal to 5. Try it. Give me a couple of the values. 3 exactly. What function are you plugging it into right now? It's out for when the velocity equals 3 or the position. Velocity equals 5 or position equals 5? You got it? What do you got? What is it? Point? 745. Any others?
1.626.
1.626. Any others?
4.129.
Okay. If you graph this function and the 5 line, you'll see it'll hit 3 times. So there's 3 times. So it'll go past 5, it'll go a little back, and then back again. So it's going to cross the x position of 5 3 times. Okay? Any questions on that? All right, let's flip to the chapter review number 67. And I want to take a look at A. Now I want to know how you would do this. Hey. Yep. That's here. Is that what it's saying? It wants the derivative of this at x equals -1. What's the derivative of that? Well, this is a function where f of x, it could be x squared plus 7. It could be 2x. It could be 0. But what is the derivative of f of x? Well, that's at a specific value. In general, what's the derivative of f of x? It's kind of a trick question. Yeah, it's f prime of x. What happens with a function when you have a number in front? How do you take the derivative of those two things? Wait a minute, how do you do this? The derivative of a function with a constant in front. What's the rule? If it was 5 times x squared, what's the derivative? 5 times the derivative of x squared. If it's 5 times x, what's the derivative of this? What? What's the derivative of 5x? 5. 5 times the derivative of this. 3 times some function. What's the derivative of that? 3 times the function's derivative, exactly. Minus, what's the derivative of g of x? G prime of x. And now you want to know what this value is at -1. Do we have enough information in this table to figure that out? Do we? What is f prime of -1? What is g prime of -1? Does that make sense, you guys? Again, whenever you have a function, its derivative is its derivative. And you may know what the function actual equation is. Question? I didn't hear what you said. Okay. Try E now. E. Try E. We don't have enough skills to do any of these other ones yet. We'll get to it. But we can do E. What's the derivative of that? Well, what type of problem is this? In general, it's a what? It's a quotient rule problem.